what I want to do today is I want to talk about the different ways in which we can represent circuits and different ways that we can prototype them. And some of that stuff we touched on last time. And so one of the things that we're going to try doing, is actually building a prototype of the same circuit that is the circuit that we use for the soldering part of this. We'll see how that goes. And so this is why it would be helpful if you, Ashley, do you have the soldering kit with you? Like, did you grab one of them last time?
The
little part thing.
No, I didn't. Don't worry about me. Don't worry about me.
Okay, it's fine. I'll ramble on for a few minutes to sort of like set up what we're doing, but then we'll also do some hands-on stuff. And then the people that are saying for soldering will say for soldering. Just for those who haven't seen the kits, what it looks like is a tiny circuit board with a couple of LEDs and a light sensor on it. And the way that it works is that when there's light shining on the light sensor, then the LEDs turn off. And when the light sensor is in the dark, then the LEDs turn on. So it's sort of a, what's the name of the bugs that come on in dark? Fireflies? Yeah. Yes. So that's what we're doing. So let me just start with some setup here. We saw this last time, and this is a sort of overview of the different ways in which you can prototype a circuit. The recap here is that going from left to right, you're going from more diagram that doesn't do anything to a physical thing that you can call hello that actually works. So on the diagram side of things, there's a sort of a convention that's existed for like 50 odd years right now for how we diagram circuit schematics. Then we can put the circuit on a breadboard, which is sort of a plug and play kind of situation that falls apart easily if you drop your circuit. Then the next level up, you can put it on a circuit board, on a solderable circuit board. And that is a thing that is more rigid and more robust, but it's harder to make changes and it's harder to repair. And then you can take those and you can have them professionally fabricated, which is sort of the most intense and the most complicated that you can get about this. And that is also takes the most time because it takes like a couple of weeks for you to send a design out and for the circuit boards come back, and it's the most expensive because you're paying for somebody else to fabricate all the stuff. And then what we're going to talk about today is mostly on the left half of this picture. We're not going to get into how to build your own circuit board, but we are going to talk about how to prototype a circuit because even when you're working with other people's stuff and reading other people's diagrams, that's useful. But then especially as you get into tinkering with your own circuits, knowing how to take a bunch of parts and make them go in some way is really helpful. So when it comes to looking at diagrams, historically speaking, the only form of diagram that we used to have was this sort of like an engineering schematic for a circuit. More recently, and to us more usefully, a thing that has started happening is that we have apps like Tinkercad that will draw these more human readable schematics for you. And here you see a human readable schematic of that same circuit that is the bug circuit that we're going to do for the soldering part of this. There's actually a typo in this diagram. There's a thing that's on backwards, so don't use this particular slide to try to make this thing because it's not going to work. But the idea here is that you have parts that look like what they're supposed to look like. So there's a battery holder. Does my laser work? Yes, not on the screen. Great. So there's a battery holder here that looks like a battery. There's a little photosensor that looks pretty much exactly like that photosensor that's in the kits. Here's some resistors that look similar to the resistors that are in the kits, etc. And the wiring, on the other hand, that is shown in this diagram, obviously is not part of the circuit of the like when you put this together, there are no wires. All the wiring is inside the circuit board, if you will. So what we're going to do in a minute actually is I'm going to show a diagram of the circuit that doesn't have the typo, so that it is exactly matched to what is on that circuit board. And then we're going to have a look at the circuit boards. I'll pull some of them out of the box and try to figure out how this diagram actually corresponds with things that are in the circuit board. Ashley, if you want to do this, we have pictures of the circuit board posted in Foundation Slack, so you'll be able to follow off of the pictures and the diagram.
Okay.
This diagram that you see here was done in Tinkercad, so this is all easily accessible to anybody that wants to play with circuits. And not only that, but in Tinkercad, you actually have the ability to, up to a point, see how the circuit would work. So I'll show you Tinkercad in a minute, but when I draw something like this in Tinkercad, I can push a button in Tinkercad and it turns on the circuit. And then what that does, for example, is like LEDs will light up. If they're correctly wired, and if they're not correctly wired, they don't light up. A not quite as useful in some ways because it is harder to read and it requires understanding more of the sort of engineering convention around this type of schematic diagram. And this is historically, this is the only thing that we had. The main reason to want to be kind of at least a little bit familiar with it is that in a diagram like this, if you go online and you start looking for tutorials, you're going to find that some tutorials will use this type of diagram. And so if you're trying to figure out what's going on, looking at a diagram like this, you at least need to be able to squint enough to figure out what's happening in the diagram. And if we go back and forth between these two for a second, so you can see that this is you have like these two LEDs in the top right corner with two resistors that are connected to them. Similarly, here in the top right corner, you have two LEDs that are labeled LED, and they have like a little lights bolts shining out of them, and you have resistors in the top right corner as well. And so all of these symbols for different parts are kind of mostly standardized. There's a little bit difference between European and American standards, but if you go on Wikipedia and you type resistor, in the info box in the top right corner of the Wikipedia page, it will show you the symbol for it. So if you ever get lost trying to figure out something like this, you just go to Wikipedia, start looking for electronic symbols, and you'll be able to like find your way through it.
Next question.
Yeah, go for it.
Okay, so R1, that's that's like a little solar panel type thing. And
Yes.
That's taking in energy.
Yes.
Are those diodes, LEDs?
Yes.
And those
yes.
are taking out energy. Q1 is
So
what?
yeah, so just to back you up a step, like if you look at these initial letters, first of all, if you look at every one of these parts in the engineering schematic, every one of them has a label in the sense that everything that is a resistor is labeled like R1, R2, R3, R4. So R1 is a photosensitive resistor. And the other three are not photosensitive, they're just fixed resistors. And so there's a convention for how these are labeled in that if you are making one of these diagrams, everything that is labeled with the letter R is probably a resistor. Everything that is labeled with the letter D is probably a diode. And in this case, it's a light emitting diode, aka LED. And as it happens, transistors are very frequently, by that convention, labeled with the letter Q. So this Q1 here is the only transistor that's on this thing, and that's the in the kit. What it looks like is the black bean with three legs sticking out of it.
It's the trade.
It's what?
Right.
Yeah, and so what it does, it's a switch. So basically, what's going on in here is if you have a look at how this is connected. These LEDs and these resistors, they're connected to the battery. So this is the plus side of this is the battery, this is its plus side, right? So this energy coming from the battery goes through the resistors and to the LEDs, and then it goes into the transistor. And so what this transistor does is it either makes the rest of the connection in the circuit so that the LEDs are connected to the other side of the battery, or it doesn't. So it acts like a switch. Now, this transistor has an input into it. This is what's happening here on this pin number 2. That input is coming from the photosensitive resistor. So this circuit really has two parts. It has a photosensitive resistor that changes its outputs based on the amount of light that it's getting, then that goes into the transistor, and the transistor decides whether to turn the LEDs on or off based on that input, right? So this is actually very common as far as any kind of circuits that take inputs and work differently, change their behavior based on those inputs, will have transistors, whether in this like, individual transistors that look like this, or like, transistors that are built into a sort of like an assembly of transistors that do something in particular. And if you wanted to, you can start with transistors like this and build yourself a very slow and small computer. And that is how computers got started, like, back in the 60s or 70s. And if you have a look at what's inside a computer today, it's basically all the same stuff, just compacted a lot. Like literally these days, inside your computer, the size of a transistor is like 1 billion times smaller than it is here, more or less, but it's still the same stuff that works in the same way. Any more questions about the general shape of this? Okay. So let me see what we got. Right. So we have the two of them side by side, which would have been useful to have. So what you see here on the right is a picture of what the conventional symbol for a thing looks like. So for a resistor, it's a squiggle. What the picture of it in Tinkercad looks like, and then what it might actually look like in person. So the blue resistors over there. Sometimes when you buy resistors, sometimes they're brown, sometimes they're blue, but they're all pretty much the same. And similarly here, you see a symbol for an LED, then a Tinkercad picture for an LED, and then what an actual red LED might look like, etc. And so as you're trying to understand some of these diagrams, what becomes important is that you're sort of doing this mental mapping of, okay, here are the actual parts that I have in front of me versus here's what they look like in the diagram, and then trying to understand how, how to wire them together. When you're wiring things together for prototyping, so when you solder them together, you're kind of done prototyping. When you're soldering, you're basically under the impression that this thing you're going to put together works. When you're trying to figure out how to make it work, then you want to be able to plug it and unplug it, and that is the more of a prototyping, tinkering with things stage of your adventure. When you're working on that, you're going to be using something called a breadboard. And so I have 5 of them here, and we have 10-ish people. So that is around 1 per 2 people. The ones that we're passing around are what's called a full-size breadboard. And what you see here on the screen is what's called a half-size breadboard. So what you see here on the screen is basically one half the size of what you have in front of you. And the purpose of these things is that they have these little sockets in them, and these sockets let you plug things in. So let's back around some more parts. Let's do this. Everybody gets 2 red LEDs, and then we'll sort of go from there. Yeah. Yeah.
That was about.
That's fine. We got extras. So what you'll see if you look at those is that the size of the sockets on the breadboard is about the same size as the size of these legs on the LEDs. So you can literally take you can have like 2 per person. Everybody can get 2 LEDs. We got plenty. Yeah.
And this is usually used for like proof of concept, kind of like
Yeah.
see if it works.
Yeah, exactly. And we'll do that as we sort of like go through this. Since there's no power attached to this right now, so nothing's going to happen. Nothing good or bad is going to happen. But you can literally take these LEDs and plug them into these sockets, and they'll stay in the breadboard until you pull them out. When it comes to actually putting circuits together, what is do we have? Yeah. So when it comes to actually putting circuits together, what you need to know is that breadboards have sort of this internal connection. So if you look at, if you look along the edge, one of the edges of your breadboard is going to have basically a row of sockets and like a red line running next to them, with a plus label on one end of this line. And what that is telling you is that all of those are actually connected together. So it's basically like a power strip. So if you plug in a battery on one end of that power strip, now you can plug in parts into anywhere else on this power strip. And you can add yourself some wires. So for example, this resistor here, the way that it is connected is that there's this wire here that starts at the power strip and then it goes this way. And then what ends up happening is that now these 5 act as like another power strip. So basically, along the edge of your breadboard, you have 2 power strips running in parallel. And then, so that would be the minus and the plus. And then perpendicular to them, then perpendicular to them, you have additional power strips. Now, these power strips only have 5 sockets. And what you do when you're working with the breadboard is you interconnect these so that you can connect your parts. So what this saves you from doing is having to put wires into everything. Because basically the breadboard comes with built-in wires that you can use as sort of extensions. So what I'm going to do here real quick is I'm going to switch over to Tinkercad, and I'm going to make myself a new circuit so I can show you what this would look like. So in Tinkercad, what you can do is you can say, I'd like a breadboard, and here's a breadboard. And you can say, I would like an LED. So here's a red LED. And then you can plug this on, in Tinkercad, you can plug it in. And so now what I'm doing here is I put this LED in like this. And what this does for me is now if I want to connect this LED to something else, I can use this column to connect that something else to this leg of the LED. And I can use this column to connect to this leg of the LED. So for example, if I just had a, let's say we're going to grab a battery, like one of these. Here's the battery. Make it. Yeah, you can attach a potato. And LEDs need resistors for reasons that we're not going to get into right this second. So what I'm going to do here is I'm going to say this LED is going to be connected to this resistor. We'll make that, I think, 300 ohms. It's a really good number. We'll connect this positive side of the battery to this. Nope. Well, switch this over here. We'll connect the positive side of the battery to this leg of the LED. This leg of the LED is connected to the resistor, and then we'll connect the negative side of the battery to this end of the resistor. Let me just scoop this around so it looks a little better. And if I did this correctly, now the LED turns on. So what I did here is rather than wiring directly to the LED, which is harder to do because I'd have to solder or clip things together, blah, 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 blah. What I can do is I can run this wire into a socket on the breadboard. And then because these 5s are all connected to each other, which Tinkercad is helpfully showing me, like when I mouse over one of them, it shows me the rest that are connected to it. By hooking up this wire here, I got power to the LED. And then I needed this LED to connect to the resistor. So I connected the LED to one socket in this column. And then I connected the resistor to the other socket in this column. So that connects the 2 of them without me having to run a wire between them. And then the last thing that I did was I took this end of the resistor and I connected it to the other end of the battery by putting a wire in here so that, again, I don't need to clip these together. I don't need to solder them together. I can just plug both of them into the same row or column. And knowing that each one of these columns of 5 sockets is internally connected, I can use that to make connections. Again? Do you want the explanation one more time or the showing you how to do it one more time?
Yeah, well, I guess.
Yeah, both. So I'll go through this one more time, but let me just see if there raise your hand if you are confused and want me to see this again, and you have questions so that I see like where to focus. Yep, okay. Okay, so we'll do, yeah. Are there specific questions people wanted to
That's a
ask?
small question.
Yeah,
So the cathode and the anode, positive and negative, would it matter if you flipped it?
it would not work if I flipped it, and I'll show you that in a second.
Well, does the polarity of the LED matter? Does it have to be a positive?
Yes, it does. And I'll show you what happens if I do it wrong. And I think there was a question maybe over there. Let me get to that in a second. Okay, all great questions. So, yeah,
You explain what the 5 minute ones are. I get how the minus and the positive are.
Yeah.
But
yeah. So let me get another breadboard up. And let me use my mouse to show you how these connections work, right? So if I put my mouse over this, it shows me that that entire row of sockets, they're all connected to each other. Okay, so if I plug in a thing anywhere over here and I plug in another thing anywhere over here, those two things are connected to each other. The same thing is true for this entire row of 30 in my case, because I have a half-size breadboard, or 60 sockets in your case, because you have a full-size breadboard. So this entire row, this is all connected to each other. Then, separately, each one of these blocks of 5 is connected. All 5 of them are connected to each other, and they're not connected to anything else. And then in the other half is the same way. So these, blocks of 5 are connected to each other, but they're not connected. Within each block, they're connected to each other, but the blocks are separate from each other. And then here I have another row of 30. Here I have another row of 30. Okay.
So if you connect anything to one of those columns, all of that column are connected.
Yes.
Okay.
Yes.
On the positive, negative side.
So let me get back to the positive and negative side in a second. So here's what I can do. Let's say that I have, we're gonna do the same thing, right? So I'm gonna take this LED, we're gonna make another one of it. And I'll put this LED here. So what this means now is that if I want to connect something to the anode side of the LED, I can connect it to any one of these 5 sockets. It doesn't matter which one. Anything that is connected to one of these 5 is automatically connected to the LED, because those 5 are all tied together. On the inside of the breadboard, there's a little clip that clips all 5 of them together. Similarly, anything I want to connect to this end, I can connect to any one of these 5, and it's going to be connected to the LED. And if I just take a battery, let's just copy paste this battery. If I just take a battery and I connect this to my LED, what's going to happen is that this LED will blow up without a resistor, and LED will burn out. And if I do that, it shows me that that's what happens. Okay. So this is the simplest, but not a very useful circuit you can try to make on a breadboard, is to just run power and ground to any 2 of these columns, and then put an LED in there, and you can burn out the LED. Okay, but it shows you how these connections work. Now, usually when you have a circuit that has more than just one part in it, like you have multiple LEDs, what you want to do is you'll frequently need power to go to a bunch of different places. You'll need ground to go to a bunch of different places. So this is why when you're doing this, what you usually actually do is you connect your positive of the battery to your long plus row, and the negative of the battery to the long minus row. Now, this doesn't turn on the LED because these are not connected to the LED, but then you take a very short wire and you run it from here to there, and you take a short wire and you run it from here to there. So now what I've done is I've connected the positive of the battery to the long plus row, and then I used a very short wire to connect it to this column. And similarly, I use the negative of the battery with this wire to the long minus row, la-di-da-di-da, and then it connects to the minus side of the LED. And now I turn that on, and the LED blows up. Correct. Okay. Does that make sense in terms of how these things connect and don't connect to each other?
It's just like a power strip in your house.
It's
You're
like
plugging it into the wall because that's where the power comes from, and then all the other things attached to it.
Yes. Yes.
Yeah.
The only thing to realize is that these the columns of 5, they don't function as a power strip in the sense that your power strip has like 2 prongs everywhere, or 3 prongs, depending on which kind of power strip you have. These only have 1 socket,
So
right?
that's like plugging in lots of Christmas lights end to end.
Yes, yes. So to go back to the, can I please redo the thing that I did to start with, right? So now we're gonna take the circuit that burns up the LED and we're gonna add a resistor to it to make it not burn up the LED. So I'm gonna take myself a resistor and I want this resistor to be connected on one side to the ground of the battery and on the other side to the cathode of the LED. And I just happen to know this. If you go online and you look up a basic LED circuit diagram, you know, that's what people will tell you to do. Like this is literally like internet and YouTube learning. I support it. So I'm going to put this resistor here. So what I did in doing that is I connected this cathode of the LED to this terminal of the resistor. So that part is all set. Now what I need to do is connect this to battery ground. And I have basically 2 ways of doing that. One of them is I can just forget that I had this here and I can go all the way to the battery and that will work. Or will it? Oh, wait, so I missed here. So that will work. But that's kind of a inefficient way of doing it in terms of wiring. You just end up with like lots of wires everywhere. So instead, what you probably want to do is, since you know that all of these are connected to battery ground, you connect to that row and then your LED turns on.
You need 1 resistor per LED.
It depends on how the LEDs are connected, but for the purpose of tonight, we're going to say 1 resistor per LED. Pausing those 2 questions for a second. Does this make more sense now? Yeah. Okay. Great.
Are you able to incorporate sensors into this?
Yes. And we're working our way up to that.
So in this interface, you're able to change the resistance level on the resistor,
Yep.
right? So if you have a physical resistor, how do you, like, how is the resistance level determined?
Right. So you buy the one that you want is the short answer to that. And this is why prototyping in Tinkercad to figure out which resistors you're going to need, but before you buy any, and then you buy some, and then you assemble it on the breadboard to make sure that it works. And then when you're happy with that, then you figure out how to solder it together. It's kind of the process of getting more and more committed, but not trying to, like, you know, just shoot straight for the end and finding out that you didn't get the right resistor. Yeah.
Can you use a potentiometer instead?
You can, but there are trade-offs in that potentiometers, which are variable resistors. So you can use a variable resistor, but they take up more space. And also potentiometer, if it's vibrating, it might change. So you might want something that is not going to change with vibration. More questions? Yes.
So I'm trying to think here, why can't you put, say that LED on just the positive line? Why does it have to have 2 separate? I don't know how to phrase it.
So the LED, if you look at the one that you have in front of you, like the physical one, it has 2 legs, right?
Why can't I make a circuit like that?
Aha, okay, yes. So the proposal here is to do this. I'm running out of desk space here. Give me a second. So the proposal here is to take a breadboard and then not to do that. Take the LED and put that LED like this. And the reason that that does not work is I'm going to redraw this in a different way. So what you did there is you basically connected these 2 things to each other. And then maybe you also connected, you know, to a battery. So let's say that you connected this to a battery. So like this, because what's happening inside your breadboard is that all of them are connected to each other. And so this is effectively the circuit that you've made, when you did that. And if you go back to some of the stuff we were talking about last week, in order for your circuits to work, there has to be a path that starts at the positive of the battery and goes through the thing that needs to do something, in this case, an LED, and then back to the negative side of the battery. And so, okay, so you're like, fine, then why don't I just like add a wire here? What that's going to do for you now is you have connected the LED to power, but you have also created a short circuit here where this wire is creating a short circuit where energy flowing out of this battery can just bypass the LED and not go into the LED at all. And because it follows the path of least resistance, it will merrily do so. So this now, you're like, okay, now we can delete that. And this is in fact the same circuit that burns up the LED because now it doesn't have the resistor that it needs. And this is exactly the same as what we did when we put that LED on the breadboard and then ran the two wires to the two sides of the LED. Yeah.
That makes a lot of sense. Thank you.
Yes. Okay. If you have Tinkercad, like a computer in front of you, etc., I 100% encourage you to like make one of these circuits that I just did. Push the start simulation button, see the LED turn on, etc. But the other thing that I want to do is answer the question in the back.
Is Tinkercad, is it a open source software?
It is on the web, so it is freely available, but it's not open source in the sense of you can look at the source and.
But it's a web-based.
But it's a web-based app, yeah. Just backing up a step here because I wasn't here for all the previous content. Did you use Tinkercad in like some of the other modules?
Yes, we did.
Yes. Okay. All right. Okay. So now where I want to go from here is we are going to talk about the bug. So let me pull up two things. First of all, let me get some box. Can you take the pull out the circuit board and adjust the circuit board of these and the path rail?
Like all of them?
Yeah. Or at least however many you got, so that as much as possible, we can have like people with circuit boards in hand. And even if you soldered it last week, I just want you to look at an untouched circuit board for a minute. And then the other thing that we're going to look at is, with any luck, my Tinkercad. So here's what I did. In here, I drew in Tinkercad the exact same circuit that is the bug. So what we're going to do is that we're going to look at this and we're going to try to understand this relationship between a circuit diagram and a circuit board. This is the thing that a bunch of people asked about last week, sort of like where is stuff inside the circuit board. We're going to talk about perf boards for a minute here because especially if you're undertaking a project in the third week that involves soldering, this is going to be useful knowledge to you. So perf board is basically a type of a circuit board that is good as the next step in prototyping. So it is laid out in a way that is similar to a breadboard, but instead of it being a plug and play thing, it is a thing that you solder things into. And so there are a variety of different perf boards. Here you see a large one with, I don't know, there's some circuit on it. There's some pictures from the internet. What I recommend when you're doing this kind of a thing, especially when you're starting, is to get a perf board that is internally laid out in the same way that a breadboard is. So that what you do then is you take your circuits that you had on your breadboard and you just literally pull components out of your breadboard one at a time and you put them into this perf board and you solder it together and it's exactly the same thing. So that you don't have to go through the mental gymnastics of how am I going to run wires between these different things now that they're not in the breadboard. So here's an example. This is a printed circuit board that has all the same markings and all the same spacing of all the things on it as a breadboard does. This one happens to be made by Adafruit, which is a New York-based company that does really good work in hobby electronics. And so if I had done this circuit on a breadboard and then and I was happy with how it works, and then I wanted to make it more permanent, all I have to do is I take my parts and my wires out of my breadboard and I just move them over to the perf board and just solder it in. And now I have exactly the same circuit on my perf board without having to like rethink all of my wiring and rethink all of my connections. Whereas if you're doing something like this kind of a perf board, you can see that this person basically used solder to sort of like hand make these connections. So like here, there's like a little bit of solder between these two things that connects them. And that's great in terms of making your circuit more permanent, but it means that as you're going from a breadboard to that type of perf board, you now need to rethink all of the connections. And I don't find that particularly interesting because I already did all the thinking about how to connect things once. And now I just need to know that when I move it to a more permanent home, it is going to still work.
Like the benefit of doing the other perf board version, you can miniaturize it a little bit. Like
You can miniaturize it a little bit and they tend to be cheaper. Like that's one of the other things is that like, I think these are like, I want to say like $3 or $4 a piece, and these are more like $1 or $2 a piece. But honestly, I'm not doing this often enough that I'm going to save a ton of money and I waste a lot of time. And then the other thing is that like, if I go to a perf board like this, if something doesn't work, I don't know if it's because I made a mistake moving it from breadboard to perf board, whereas with this one, I can feel pretty confident. And then the other thing is that if you are starting in Tinkercad, and so you've done the Tinkercad breadboard thing, you can literally hold this up to your screen and do a visual comparison to see like, are things in the same place? When I do this, what I actually do is I'll go through my circuit and I will just count like the number of wires. That's like an easy quick check to do is like, does my circuit have the same number of wires in Tinkercad as it does when it's on the breadboard and then when it's on a perf board? And if it doesn't, then clearly I forgot a wire somewhere. And that's much easier to do if you can like hold it up and count the wires because there's one-to-one correspondence. Yeah, so that is sort of the next step. And if you're doing, and I think most of you are doing a circuit that involves it starts for your project next week. You'll be doing a circuit that involves soldering. All of them have a Tinkercad design as a starting point. So all of them you'll be able to take all the parts and assemble them on a breadboard and then put them on a perf board and really go through that whole process. So let's see. As things get advanced, what you can do is you can use software that basically lets you convert a schematic into a circuit board. So this is something that Corey did a lot of when he was working on the new circuit boards for the card readers downstairs. And I collaborated with Corey on this. And so what this ends up looking like is you start with a schematic like this one. So this is actually literally like one part of the schematic for the card readers. And then in this app, you lay out like where all these parts are going to go on the circuit board, and then you lay out where all these connections are going to be on the circuit board. So you can see, like, for example, let's do something like these little things over here, like they are all resistors. So there's like, like an easy like 20 plus resistors on the circuit board. And like all of their connections are individually drawn like in this design. And then over here, there's some things that, they're sending more power. So like these wires needed to be thicker. So basically on a circuit board sense, like the thickness of those lines on the circuit board ends up being bigger. And this here is a computer rendering of what this will look like when it has been fabricated. Actually, this side is a little more useful because this here is showing you the same side of the board as this. So here you can see that in this computer rendering, you can see like there's like tiny resistors right here corresponding to tiny resistors right here. And there's these two capacitors corresponding to these two capacitors. And there's this chip that is oriented at like 45 degrees. That's this, etc. So you go from a schematic to a representation of exactly what the circuit board will be like when it's made, to a 3D picture of where your parts are going to go, because you can easily create problems for yourself where you like have two parts that are relatively big, but you made them overlap. And then like when you look at the 3D rendering, that's when you would realize that. And then you send these designs to a fabrication company and they send back to you. You have three options. They can send you back the circuit board itself with nothing soldered to it. You can pay them extra and they will install, they will solder some parts in for you, or you can pay them even more extra and they will solder in all the parts for you. So you can just get like a finished circuit board. These are some of the names of the companies that do this. JLC PCB and PCBWay are big Chinese PCB manufacturers. They are relatively cheap, but they have relatively long lead times. Oshpark is a US-based company. They are more expensive, but they give you like more options in terms of what color you want your board to be and stuff like that. So there's like also like weird little trade-offs about what kind of quality of thing you're going to get. And typically you end up paying something in the ballpark of like $4 or $5 per square inch of boards, and you get back like three to five boards is sort of like the minimum order that you can make. So if you're doing anything where you need like several pieces of it, like we are with the card readers, you order them and then they end up being like ballpark like $1 per square inch kind of pricing, or less if you're ordering even more.